Hi, I'm Tirmazi and I'm here to introduce you to the next generation of Google Borg. We'll be taking a look at it through the lens of some cluster traces which we've released publicly. What is Google Borg? Well, Borg is basically Google's internal cluster manager, which is used to schedule jobs and tasks and all of these things which I'll describe later. In Borg speak, a cell is basically a set of machines managed by Borg as one unit. Now, if you're a user, you would submit work to Borg in the form of jobs. And these jobs will be divided into one or more tasks. Tasks will run on machines. Now, some of these jobs may run in an alloc set, which basically means that all of its tasks run in alloc instances. An alloc instance is essentially a resource reservation. Each job in Borg has a priority, and this priority affects the way that Borg schedules that job. So for the purposes of this paper, what we've done is divided jobs into different tiers based on their priorities. In decreasing order of priority, these tiers are production, best effort batch, mid, and free. Now, Borg is a large and complex system, and there's obviously more to it than what I've described here. So if you want more details on how Borg works, take a look at Large-Scale Cluster Management at Google with Borg, which came out in Eurosys 2015, and it was written by John Wilkes and others. I mentioned how we're releasing public traces as part of this project. What are Borg traces? Borg traces describe the workload in a Borg cell. So this includes the arrivals and departures of jobs, allocs, etc., and the scheduling decisions Borg takes on them, including evicting them or assigning them to machines, etc. Similarly, it also includes a measure of how much resources Borg allocates to each task and how much of those resources the task uses. This is not the first time Google has released Borg traces. There was an earlier version in 2011 which described the workload of one cell. So what's new about this updated set of Borg traces we've released? To begin with, we're releasing a lot more cells than the 2011 version. So we have 8 cells over the month of May 2019. And these 8 cells have an aggregate of 96,000 machines divided over 3 continents. Another thing I found really exciting is the fact that we are now reporting CPU usage histograms instead of just the average usage by a particular task in a particular time period. Now, what this means is that you can go and look at the instantaneous distributions of CPU usage among tasks. MapReduce and other similar applications have this sort of master-worker relationship between its jobs, and it was difficult in the previous trace to understand this, so we've included the information on a job's parent in the most recent release. Finally, this recent trace has information on how jobs use this thing called autopilot, which tries to predict the resource usage of jobs. Let's take a look at how much Borg cells are being used by jobs. There are 2 important metrics to look at here. The first one is the resources used by a particular job, while the second metric is the amount of resources Borg has allocated to that job. This plot shows the compute used by jobs in a cell in 2011. The x-axis here is the time in days, and the y-axis is the resources used as a fraction of cell capacity. Now here's the exact same plot for 2019. Notice that the 2019 plot has a mid-tier, while the 2011 plot does not. An interesting observation, especially when you think about it from a utilization perspective, is the fact that there are a lot more best effort batch jobs in 2019 as compared to 2011. All of this is in aggregate. So for example, for 2019, it shows the aggregate among all 8 cells. But we also need to take a look at the variability in between individual cells. Now let's take a look at this plot, which shows how each individual cell, including the cell from 2011 and the 8 cells from 2019, are being used by jobs. While we did see a general trend in the previous slides, it is really striking how high the variability is in between the workloads in these individual cells, and how the utilization differs from one cell to the other. In fact, if we take a look at the ratio between CPU usage, which is on the left-hand bar over there, and memory usage, which is that right-hand bar, there's also variation in between these ratios. So in 2011, for example, you could have concluded that the memory was maybe used about the same amount as CPU for most of these jobs. But if you take a look at the rightmost cell from 2019, the memory usage is almost double the CPU usage for that cell. What about our second metric, which was how much resources are allocated to jobs by Borg? Here are two plots for 2011 and 2019 that have the same axes but show the amount of resources allocated by Borg to jobs in a cell as a fraction of the cell's capacity. So notice how for both 2011 and 2019, the allocation actually being larger than the cell's capacity is almost a regular occurrence. For 2011, we see that it can go as high as 1.25, while for 2019, it can go even higher, all the way to 1.50 or above. The takeaway here is the fact that cells in Borg are oversubscribed, and the rate of this oversubscription of cells has actually increased in the past 8 years, and cells in 2019 are a lot more oversubscribed than they were in 2011. If we take a look at the memory allocated to jobs, this oversubscription is even more drastic. For example, in 2019, the memory allocated to jobs is twice as much as the memory allocated in 2011. When we look at the CPU and memory allocated to jobs for individual cells, we see, just like we saw for usage, that the variation between memory and CPU allocated for individual cells is really high. We've spent a lot of time analyzing cell utilization. Here is the big takeaway message from all of that analysis. I've shown you both of these plots earlier. So the plot on the left is the resources used by jobs, both for the 8 cells in 2019 and the 1 cell in 2011, which is all the way to the left. Similarly, the plot on the right shows the resources allocated to jobs for individual cells. Take a close look at the 100% capacity line that is spread across the middle of both of these two plots. So if you notice from the allocation plot, Borg is oversubscribing a lot more aggressively in 2019 as compared to 2011. However, if you look at the resources used by jobs from the plot on the left, you'll see that jobs are still not reaching the capacity of the cell. In other words, jobs really do ask for more resources than they use. To recap a little bit, we've analyzed Borg from the perspective of Borg cells, which is a very top-level macro way of looking at things. However, in a Borg cell, it's not like every single machine is treated the same way. So to get a better understanding of how things work at a smaller granularity, let's take a look at individual machines inside Borg cells. Keeping that in mind, let's take a look at how individual machines are used by jobs. So here's a plot that shows machine utilization on the x-axis and the probability that the utilization is greater than x on the y-axis. In other words, this is a CCDF of machine utilization. The line I'm highlighting in pink represents the machines in the 2011 trace, and the other 8 lines represent the machines in the 8 cells of the 2019 trace. In 2011, the median machine was about 30% utilized. In 2019, on the other hand, the median has gotten a lot higher, and machines are utilized anywhere between 50 to 77%. In other words, machine utilization has improved significantly in Borg. Now we know that the machine utilization is increasing over time, but does that also mean that the number of tasks scheduled to jobs is increasing? Well, let's take a look. Here are the tasks submitted per hour. Again, just like the previous slide, this is a CCDF. The x-axis here is the number of tasks submitted per hour, and the y-axis is the fraction of tasks which exceed that x value. And we notice from this plot that the number of tasks submitted per hour, or in other words, the scheduler load, has increased 4 times between 2011 and 2019. One of the most mind-blowing observations we've had during our analysis of the trace is with regards to its variability. So for variability, we're using this metric called c-squared, which is the ratio between the variance and the mean squared for CPU hours or memory hours or whatever other metric you want to measure. Now let's add some historical context to what the c-squared values for CPU hours looked like for traces in the past. A study of the CPU hours of Unix jobs in 1996 showed a c-squared of about 50. Similarly, a 2005 work analyzing the CPU hours of supercomputing jobs showed a c-squared of 250. Now let's compare this to what we see in Google's traces. So in the trace from 2011, we saw a c-squared of 8400 for CPU hours. For 2019 though, the c-squared recorded becomes larger than 23,000. This is the largest c-squared value recorded for any published cluster trace, and it has really big implications for scheduling and cluster management. To understand these implications, let's begin by introducing a little bit of terminology. So we call the largest 1% of jobs in our cluster hogs, and we call the remaining 99% of jobs mice. What we are interested in here is the fraction of resources consumed by these hogs, i.e. the largest 1% of jobs. Prior work has shown this to be as high as 50%, but at Google, we see that in 2011, it was over 97%, and in 2019, it was over 99%. This leads us to seek a better understanding of how each job consumes resources over time. So here's a graph which has CPU hours or RAM hours on the x-axis and the fraction of jobs whose CPU hours or RAM hours are greater than X on the y-axis. In other words, this is a CCDF of job resource consumption. We have 4 lines on this plot. The dotted lines belong to the 2011 trace and the solid lines belong to the 2019 trace. Also note that the y-axis and the x-axis of this plot are log scaled. The tail of the 2011 CPU hours plot is almost a straight line. We discovered that it is Pareto distributed with an alpha value of 0.77, which means that this distribution is extremely heavy-tailed. Doing a similar analysis for 2019, we noticed that its distribution is even more heavy-tailed with an alpha value of 0.69. In other words, the distributions are getting more heavy-tailed over time. We've discovered a set of very interesting observations with regards to Google's workloads. Now, what implications do these observations have for scheduling with Borg? To begin with, since we've observed that Google's workload has a high variability, in other words, its c-squared is really high, what can actually happen is you have a cell and a hog consumes most of the resources in that cell, leaving very little of those resources for the mice. So Borg needs to find a way to prevent hogs from consuming all the resources so that the mice are satisfied. We have learned a lot of new things through the course of this talk, so here's a quick summary. To begin with, there's a new Borg workload trace out. It has 8 cells from the month of May 2019. It's about 2.4 terabytes of data, which can be accessed through BigQuery, and it is available at the URL over here. Secondly, the workload and machine utilization for Borg has increased dramatically between 2011 and 2019. Finally, the disparity between hogs and mice, which is the largest 1% of jobs as opposed to the remaining 99% of jobs, is more extreme in the 2019 Borg trace than in any other reported trace. In particular, the largest 1% of jobs in Borg consume over 99% of the cell's resources. I hope you found this interesting and I look forward to your questions. Thank you.